Hello guys, welcome back, PK here. So in this video, I'm working on this interesting integral to find the generalized rational expression as a part of the result of it by using complex analysis with contour method and residues, so stay tuned. Okay, here's the question. The question is evaluate this integral from 0 to infinity cosine of x over 1 plus x squared to the power of n dx is qn times pi over e, where n is an integer and qn is a rational expression. So the goal is to have some generalized rational expression on the right-hand side. So we will be using complex analysis, contour, and the residue. So let me rewrite this integral first. So the integral from 0 to infinity of cosine x over now 1 plus x squared to the power of n dx. Okay, this is the same as now then 1 over 2 times integral from negative infinity to infinity of your integrand. Okay, then let me rewrite this again because we're using complex analysis, right? So that's why this is the same as then 1 over 4. Okay, 1 over 4 times integral from negative infinity to now positive infinity. Okay, then the integrand has to be now e to the power of ix. Okay, then we have plus e to the power of negative ix. And then that divided by your denominator still. 1 plus x squared to the power of n. Okay, then we have dx. Okay, then let's talk about this integral from negative infinity to infinity e to the power of ix over 1 plus x squared to the power of n, right? So we're interested in integral from negative infinity to infinity and e to the power of ix over 1 plus x squared to the power of n dx. Okay, then this has to be the same as integral from negative infinity to infinity still. Then this is now e to the power of, let me change this x to the z, right? E to the power of I now z. That over, okay, 1 plus now z squared to the power of n, and then we have dz. Then at the same time, we can represent your z as now this x plus I y. And then, so that's why e to the power of now iz. This has to be the same as now then e to the power of ix, again, that times e to the power of negative y. Okay, then we can easily say this e to the power of negative y, this is decreasing when y is positive. So time to use the contour. So let me draw the semi-circle. Okay, negative r, then we have r. Then we should have this now z is equal to I now. Then we are working on now e to the power of iz. Okay, e to the power of iz over z minus I to the power of n times z plus I to the power of n. So we can say this is going to be the pole of order n when z is equal to I, right? So pole of order n at c is equal to now I. Then at the same time, with your f is going to be this e to the power of iz. That over z minus I to the power of n times now z plus I to the power of now n. Okay, then based on this word, we can talk about the residue, right? So talking about the residue, okay, this is going to be then 1 over now n minus 1 factorial. Okay, that times the limit, of course, your z. Okay, the z has to be going to now I. Okay, then after this, we should have now d to n minus 1 over now dz to n minus 1. Okay, then that times z minus I to the power of n times f of now z. If you rewrite this, then it should be the same as 1 over n minus 1 factorial. Okay, then that times now this d to n minus 1 over dz to n minus 1. Okay, then that times now this e to the power of iz. That over z now plus I to the power of n. And then we have, this is going to be at when your z is I. Okay, so that's why we can talk about this integral from negative infinity to infinity, e to the power of iz over 1 plus z squared to the power of n dz, right? So, integral from negative infinity to infinity. And then we have e to the power of iz over 1 plus z squared to the power of n, and then dz. This can be rewritten as 2 pi I. 2 pi I over n minus 1 factorial. Okay, then that times d to n minus 1 over dz to n minus 1. Okay, that times e to the power of iz times z plus 1, so z plus I, to the power of negative n, at where at your z is now I. Okay, now we can use Leibniz product formula. So if you're using that, this d to n minus 1 over dz to n minus 1 is e to the power of iz. That times z plus I to the power of negative n. Okay, then using the Leibniz product formula, we can rewrite this as now summation from k is equal to 0 to n minus 1. Okay, and then that times binomial with n minus 1 and k. That times, let me make a parenthesis. Then we have d to n minus 1 minus k. That over dz to n minus 1 minus k. E to the power of I now z. Close your parenthesis. Okay, then we multiply d to k over dz to k. This z plus I to the power of negative n. When your z is equal to now I, right? Taking one more step to rewrite this, then this has to be the same as still summation from k is equal to 0 to n minus 1. Okay, and then also binomial n minus 1 with a k times I to the power of n minus 1 minus k. And then that times now e to the power of negative 1. Okay, then that times d to k over dzk. This z plus I to the power of negative n when your z is equal to I. Okay, now we can talk about an expression of d to k over dz to the power of k, z plus I to the power of negative n. So d to k over now dz to k. This is z plus I to the power of negative n. Okay, so this is going to be the same as negative n times negative n minus 1 times all the way up to negative n minus k minus 1. Okay, and then that times negative, so 2I to the power of negative n minus k. Of course, and z is equal to I. Okay, so that's why now we can get this summation sign. So we can represent this as now summation. Say from k is from 0 to n minus 1. And then that of binomial n minus 1 and k. And then that times now I to the power of n minus 1 minus now k. And then that times now e to the power of negative 1 times everything. Negative n times negative n minus 1 times all the way up to negative n minus k minus 1 times 2I to the power of negative n minus k. Okay, so that's why if you take one more step, then this has to be the same as summation from k is equal to 0 to n minus 1. Okay, then we have still this binomial n minus 1 and k. Okay, then that has to be the same as 2 to the power of negative n minus now k. Okay, then that over now e, because we have e to the power of negative 1. So that over now e. that times I to the power of, say, n minus 1, n minus 1 minus k. Okay, then that also minus n minus k. Okay. And of course, that times now this negative n times all the way up to negative n minus k minus 1. So that's why if you take one more step to finalize this expression, then it has to be, we can pull this 1 over IE out. Okay, then we have the summation from k is 0 to n minus 1 with this binomial n minus 1 with k. That times now this 2 to the power of negative n minus now k. Okay, then that times, we can pull this alternating sign out. Negative 1 to the power of k. Okay, then that times now negative n times all the way up to negative n minus k minus 1. And if you rewrite this part, okay, this part has to be the same as then n times now n plus 1 times all the way up to n plus k minus 1. It's the same expression. So now we can go back to this integral from negative infinity to infinity, e to the power of iz over 1 plus z squared to the power of n and dz, right? So you're working on integral from negative infinity to infinity, e to the power of iz over 1 plus z squared to the power of n and dz. This will be the same expression as then, okay, 2 pi I over now n minus 1 factorial. Okay, then that times 1 over IE. Okay, 1 over IE, that times summation from k is now 0 to n minus 1 of binomial with n minus 1 and k. Okay, and at that times 2 to the power of negative n minus k. Okay, then that times n plus 1 times all the way up to n plus k minus 1. And then we already know the formula for this, right? The combination formula. So that's why this part, this is the same as n minus 1 factorial. That divided by k factorial times n minus 1 minus k factorial. So using this, we can also rewrite that expression as, okay, say 2 pi over e. And then that times now 1 over 2 to the power of n. That times summation from k is from 0 to n minus 1. That times that expression, n times n plus 1 times all the way up to n plus k minus 1. That over, denominator has to be simply k factorial times n minus 1 minus k factorial. And of course, you need to multiply 2 to the power of negative k right next to it. And at the same time, we also know this integral from negative infinity to infinity, e to the power of negative ix over 1 plus x squared to the power of n dx. This is the same as integral from negative infinity to infinity, e to the power of ix over 1 plus x squared to the power of n, and then we have dx. So that's why this original integral that we are working on. Integral from 0 to infinity cosine of x over 1 plus x squared to the power of n dx. Okay, this has to be the same expression as now then. 1 over 4 times now 2 times 2 pi. That over now e. Okay, then that times now this 1 over 2 to the power of n. That times summation from k from 0 to n minus 1. That times now everything, right? That times everything. N times n plus 1 times all the way up to n now plus k minus 1. That over k factorial times n minus 1 minus k factorial. And then, of course, that times 2 to the power of negative k right next to it. Okay, so based on this work, the generalized rational expression on the right-hand side, let me just pull this pi over E out first. Times, let me make a bracket, and we have now 1 over 2 to the power of n. Okay, then that times summation from k is equal to 0 to n minus 1, that of n times n plus 1 times all the way up to n plus k minus 1. Okay, then that over k factorial times n minus 1 minus k factorial. That times 2 to the power of negative k. And then we can say this bracket has to be your Qn, right? So this has to be your Qn. That is rational expression. Because it's a pretty interesting integral to evaluate. So I'll be back with more videos, more questions like this sometime soon.